It's here, right? Yeah.
Okay, morning all. First part of today's show and tell is a demo of interacting with the fidgets through an Android device. Very related to what you're doing in terms of your assignment. I've got a little sort of display screen of control of things on here that's going to pick up things on a little board that we put together. The board's got a Raspberry Pi as the main controlling processor. You've got your usual RFID reader, a collection of the sensors going through that sensor board that you're aware of. Some motors. Generally the motors that you've got are just single motors with a board. This is a bit of an upgraded one. It can control 8 motors simultaneously, and I've got 4 on there to sort of work. I sellotaped onto or plastered onto it, just so you can see perhaps the motors turning at the back. I've taped a pen onto motor button number 4. But to give you a sort of idea of working through it, some of the sort of things that are happening, that should be the display. So if I ask motor 1 to turn, that wouldn't sound too healthy. It sounded like it was skipping on motor 2. It's hard to see sort of back there, but if I turn motor 4 is on a little slider there, so I can use the slider control to turn the motor to a particular position. I appreciate we can't sort of see it too well necessarily at the back. I might try and bring it along to some of the labs to sort of work with. On or off for the first 2 motors to sort of put them back. Looks like motor 1's just packed in. Some of the other things built into it, the RFID scanner there. Got a little tag to it. You'll have to believe the number, hopefully, that comes up. So that's picking up that's sending out the tag ID. and when it loses it to redisplay. All this done using MQTT to send the sort of messages to and from. The actual MQTT server's on the Pi itself. So the lights, these will be quite difficult to see. These are just lighting up the LEDs. So LED 2, 1. The hand-fisted on my fingers there. That should certainly be the least lighting. Oh, no, it's not coming on. Like any great live demos, things fall apart. LED 4 on. No, none of the lights seem to be coming on. I need to sort of check that. Some of the other values, so we've got the slider and the sort of rotation one. Hopefully, these will be okay. The rotation one there, as I'm moving it sort of round. I'll do the slider one, but at some point the the actual moving knob sticking out has broken off. Vibration sensor though, as I'm sort of tapping it. Touch sensor, that force sensor is like that blue one that you've got in the kits. Where's my force sensor? Oh, I have to display that one well enough on it. Yeah, just below touch. So as I sort of press my finger on the blue force sensor, they're just sort of going up. Now all these are connected just in the same way as what you're doing in the lab sessions. They're all connected up to one of the sensor interface kits, just on different channels. Those channels broadcasting out whenever a sensor change occurs. And the Android device, it's not sort of physically connected to it. Android device picking up on that MQTT publish topic, subscribing to the appropriate topics and displaying the values on its on the screen. So it's all, it's only sort of simple interface there. It's really just a demo one. As I say, we maybe sort of change again the position of motor 4. Then the look should have sort of moved over to a particular position. I just wanted to give a demo of what your final sort of piece of work is going to be looking something like to sort of work with. If anybody wants to sort of come and have a look at this sort of thing, anytime you sort of call them by the office, you can sort of have a live demo of that. I'll try and bring it along to 1 or 2 labs. It's a bit of a thing to lug over with it. Another thing that I want to sort of pass around and have a look at is this. Not much to sort of, as it comes round, it's not exactly a huge thing to look at, it's just a big, sort of look like a big hockey puck, something like that. I'll just bring it up on the screen for what it is. This is one of the door lock controllers that's sort of commercially available for smart door lock, manufactured by a company called August. There's quite a few of these out now. Yale do their own sort of versions. But basically it's just a motor inside it, like a servo motor. You'll feel it's quite heavy because it's self-contained. It's got its own battery supply of 4 AA batteries in it, so it can be sort of quite weighty to it. And it just fits over a little spindle coming out from your lock. And to sort of see it working, we have a little sort of demo video.
Safely and securely, starting with August Pro. August Door lets you see and speak to guests right from your phone.
Ryan! Yes, I can see you.
A built-in floodlight and HD color video lets you see your guests day or night.
This is an older version, this one doesn't have floodlights.
Hey, it's me.
Sometimes uninvited guests can pay a visit. Anytime motion is detected, a floodlight is triggered and an alert is sent to your phone. And if you miss an alert, don't worry. You can play back the full story later. With August, never sacrifice convenience for security. August Smart Lock lets you and your friends securely lock and unlock the door using the August app. The more physical keys you have, the less secure your house is. Keys can be lost or stolen and then easily copied. August lets you easily create secure temporary keys for your friends, family, or people you trust right on the August app. Grant access for a few weeks, a few hours, or forever. You decide. Once the set time ends, keys are automatically deleted so they can never be reused. Want to know who's coming and going? Activity Tracker lets you know who's coming and going 24/7, so you know when loved ones are home. And with DoorSense, you'll know your door is both closed and locked from anywhere. Never worry if you closed your door again. All August smart locks not only inside of your door, so the street view of your door stays the same. Our smart locks use band-grid encryption for wireless communications, ensuring a secure lock. Make your front door more secure with August. August, the key to your smart home.
No, I'm not actually employed by August or anything like that for it. I've got a couple of these on my house to work with. I'm quite taking the plunge and put it right on the front door. I've got them on a couple of the rear back door sort of things to get in. But it's just a souped up version, again, of what you're doing in your assignment. It basically turns a servo to it according to what the user presses in their app. It doesn't use Wi-Fi for it. It doesn't go over the internet for it. Although you can get those extensions. This works with, I'm fairly sure it's Bluetooth, so you have to be within a certain range of it. But it's the same sort of idea. Sending a message to the lock, telling it to undo. You can put all sorts of things like encryption in it. You can give people access at certain times of day, so that when they click the button, it will open it. So you've got, say, I don't know, cleaner coming in or something like that. You can grant them access at 2 till 4 on a Wednesday afternoon to sort of work on those sort of lines. Bear in mind, I mean, this is a commercial product sort of thing, so it's somewhat beyond what we're doing in the assignment work, but it's the same sort of principle going on in the background. They sell like an extension part to it. This works, as I say, really over Bluetooth, but you can get a plug-in module that enables sort of internet connection really quick then, and then that hub talks to the actual sort of lock itself then from it. The lock by itself doesn't communicate directly there. But as it comes around, just sort of have a sort of look at it, see what it's about. You'll feel, as I say, that it's quite heavy, and it sits on the back of your door to sort of do that turning. But similar ideas to what you're doing just there in the assignment. Okay, what we're covering this week, getting on to intelligent data processing. The labs, there's no specific lab to be doing. It's really Action Week. The people who were in yesterday sort of got aware of that, and hopefully you're already aware of it. So it's continue on either with the Android lab from last week if you didn't manage to finish it, or some of the previous labs to sort of work on. Or if you've sort of done those, you're working with myself and Ryan over there to perhaps sort of help out with some assignment-related questions. It's just basically you'll have access to that kit for that much longer. Next week is Tutor Week, so there's nothing going on next week in terms of labs and lectures. But the week after is going to be another catch-up assignment that we'll have to be working on. We'll try and give you plenty of time to be working on that. Today's session, though, I say intelligent data processing. I'm looking at alternative sensor types as well. Come on, ready? Go. Intelligent data processing to say, well, once we've collected this data, we've looked just in the past few weeks at the actual sensors, if you like, and how they sort of pick up, and perhaps a bit on that network side. But once you've got that data, what are you going to do with it? And we've got this sort of sensor network, perhaps, the parts over on the left-hand side, the individual nodes, to be sort of working with, perhaps going through what we refer to as a sync node that might collate the data in some ways. These other ones are just sort of data collection parts and send the data over to the sync node, may or may not be there, but then a gateway to the actual outside world. You've got this sort of thing implemented on your PCs, where your PC is the everything node in some ways. It's got all these sensors connected to it, but it's also a gateway. That's not a typical case to sort of using these sensors. Generally, the sensors are very low profile, so a very low footprint in terms of the processor that they're using, the memory space they're using, the power that they're using, and they're sort of communicating between themselves to work with. When it comes down to your assignments, this is sort of how you might envisage, say, even something like a lawn sprinkler network, which is what you're basically designing. The small sort of bits over on the side of the bits scattered out around the greenery, if you like, each individual sensor having perhaps a motor in it to open the valve, perhaps a soil sensor to detect how dry the soil is, maybe an atmospheric sensor attached to it, but they've all got to sort of relate back to decide when to turn on. So your sprinkler system in this case, and it could equally be a home heating system. But each one's got to decide when to turn on, either a certain time of day or certain conditions when the soil's at a certain dryness, or it's a hot sunny day and has been for 2 days or something like that. You might have to do some bits of processing before you actually activate that actuator, the motor, or do something with it, because it might be based on historical data and who's going to contain that. Now we're going to have a look at some of those sort of aspects today, and some of these aspects may well come out in that design that you're doing for the assignments. Not just the actual sort of node layout, but how you're going to process that sort of data. What sort of operating system is on these devices? What protocols are they using to talk to each other? Are they using Bluetooth, Zigbee, Z-Wave, Wi-Fi? What sort of protocols are working from the gateway to sort of to access the sort of internet? So these are the sorts of questions that you're going to be answering in that task 3 of your assignment. So both information from previous weeks when we looked at nodes, it's going to specify what sort of node level you like, and today when we're looking at sort of how you might link these things together. Because there might be a bit of processing going on, either on the actual node itself. It might just be a tiny processor, but is it going to broadcast out its data immediately, or is it going to do some perhaps aggregation before it sends it out? Is it going to average the data? The sync node might be bringing together a collection of values before it sort of talks out to the sort of internet. We're going to have a look at what this in-node and aggregation processes are. Now they're generally application dependent. Whichever application you're writing, they'll sort of depend on that. But the sensors themselves are generally fairly inexpensive. Yeah, for a prototype system, it may sort of cost much. You might sort of evaluate how much your prototype's going to cost, and it comes to £150 or something. But once they get into mass production, generally these sensors or actuators are fairly low cost, they're supposed to be. Normally a low data rate for transmission, some sort of radio transceiver for sending that over, whatever protocol you're using. And they coordinate together to perform the desired task, whether it's heating your house, monitoring an outside environment, sprinkling your lawn, whatever sort of task they're sort of working on. And the acquired information might be periodic, say you're taking every hour, every day. It might be event-based. When you detect that it's raining, do something. When you detect the temperature reaches a certain level, do something for it. So it all just really depends on the actual application that you're dealing with. Now, just as an aside really here, the sensors we've been looking at have all been sort of plugged into your node in some way, working with an actual sort of processor, temperature sensors, movement sensors, all that sort of thing, or actuators, lights turning on. There's alternative sensor types that we may not have considered, particularly things like using a human being as a sensor for it, a citizen sensor, if you like, where we can pick up on things that people in general are reporting. Presumably, you yourself are forever sending out messages. You're on Messenger, you're on WhatsApp, you're on Twitter, whatever sort of thing. Now, those can contain bits of interesting information, because when you tweet something or when you send a message out, often your device is linked into your location as well, particularly if you would Google, say. And so, like, every message that you send doesn't work just with the actual message that you want to send, or the video, or the image that you're sending. It's also going out with your latitude, longitude, who you are, and perhaps when it gets to the other side, to the server, all your history of that sort of thing. So we can get a lot of information out from that by sort of tweeting real-world data in a simple instance, just of these things like Google Maps do. When you ask Google to give you a map and give you directions, it can sort of predict where there's, or seemingly predict, where there's traffic jams. And so you're getting your display on your maps, and it's showing a road in red about 4 or 5 kilometres ahead. Now that's relying on all these other cars all having their Google device turned on, broadcasting out their location, and Google can keep track of how fast these are moving. Know that the typical speed of people on a motorway, let's be nice and call it 60 or something like that people are going along at. And so when the average speed of an individual seems to drop to 10 miles an hour, then it looks like, well, wait a minute, there's probably something sort of going on there. Let's, at this particular point, and there's a lot of cars in the same situation, let's indicate that that's a traffic jam to sort of people behind. So you're acting really as a broadcasting out for the common good, almost there for it. Now that can be done in a variety of situations. We can have a look at, say, tweet data for it. I'm using a technique called sentiment analysis. Some people may be doing this as part of their project. What sentiment analysis is looking at the actual phrases that people use and deciding whether that's perhaps a negative comment or a positive comment. Like, some people might say, oh, what's your opinion of the mobile app development sessions that you do? Oh, they're really boring. Oh, we never actually sort of do it too hard or something. That's seen as a negative comment. And how do you know it's negative? Because of the phrasing that you're using. You know things like boring, hard, never do this. They tend to be expressed in a negative way. Whereas people who are saying, yeah, GrepCon is really interesting. It really looks sort of relevant to what we do. So relevant, interesting, come out as being positive ones. And then we can analyse not just sort of tweets, but messages going about. We can do sort of the sentiment analysis on these sorts of things. So if we look at that particular link, I've brought it up in the browser here somewhere. Sentiment analysis chart, really, that we can sort of come up with. And look, you can see there that it's sort of spread out around people who are being sad, unhappy, depressed, bored in one sort of area, completely the other side, alert, excited, those sorts of things. Now, I could type what are the keywords to look for. Probably going to be, if I put mobile app development in, I don't think there's many people around the world going to be tweeting about that. So if we put something in that's fairly sort of relevant, let's look at what's sort of going on in the world out there. And I'll put the, say, the news. So some of the things just sort of going on out there. Let's look for a sort of keyword that people might be tweeting about. Some of these things I don't necessarily want to put out there. I'll do sort of a fairly easy one. Let's look what people are currently tweeting about, say, Trump, for a sort of keyword. Now this, you can alter it, but this gathers a certain sort of data set of comments done in a particular time. It's sort of showing really where the comments seem to be lying there for it. currently perhaps they seem to be down in this contented, serene, relaxed, calm area. And if you think about it recently, he's not said anything that controversial in the last 2 or 3 days, so it might sort of be up there. We can see other ones being out to the different places. They are really what types of words that people are using when they mention this keyword Trump, say, in it. Perhaps let's sort of choose a different one. I'm not sure when you'll come up with this. Halloween. Try and guess what it's going to be. Hopefully I might get a few people excited about that. But, no. I think it's like the Trump one to me. Oh no, it's more, there's less on that left-hand side. But overall, the idea of Halloween doesn't really have much stress about it. Not many people are negative about Halloween, but it's just a bit of a joke festival going on with it. So you don't get many, you get a few people perhaps who are bored, that sort of thing. Not many people who are sad or unhappy over it for that. Now, what does that mean that you can do in terms of like a sensor sort of thing, a sensor analysis? Well, it means that like if people aren't sort of happy about something, you know you're doing something right, hopefully, or that might trigger off certain activation of things. You know, not necessarily turning a motor, turning a light on, but it might trigger some sort of good activity to take place. If people are down in that stressed, nervous, upset area, perhaps you might want to sort of do something about it, and or it might be the case that it's automatically triggering something or not. The general idea is that we're saying that these sensors don't have to be electronic, mechanical devices. It can just be picking up on everyday activities that people are doing, and you're all contributing to that. Because you know, nobody's going to kid themselves that their messages aren't being stored by Microsoft or Google or whatever. Yes, all your conversations are being stored, not personally because they want to learn more about you. They want to learn about trends and where things are going, for it to be able to sort of do that analysis and look at things overall, how they're working out. So I mean that's one particular aspect that we sort of can look at. All these terabytes of tweets that are flying out, terabytes of instant messenger things that are sort of going through. There'll be similar ones for other ones there. Or say there's a big push for having smart meters in houses. So the government's under pressure, or pressurising the energy companies to get these smart meters installed in people's houses so that we can better predict and balance power consumption. So if we know that, as we've sort of hopefully known for years before TV streaming came in, say the vast majority of the nation watches EastEnders or, well, let's pick Coronation Street. Millions of people watching Coronation Street. I don't know, not you perhaps sort of thing, but and then during the advert break, we get this old sort of thing of people get up and make a cup of tea, power consumption zips up. So they're ready for that already in terms of the power companies. They do monitor things like TV schedules. It's getting a bit harder now with people streaming and not necessarily following traditional watching habits. But if we can sort of try and predict where things are going, where power consumption is sort of happening, what times of day it is, who's using what, we can make things like intelligent fridges or intelligent freezers, say, that when there's a peak demand, they want a low energy usage. So the freezer might sort of say, okay, I know there's a peak demand, I'm going to actually just turn off my motor for 2 hours. Now that's not going to save you a huge amount of money, but multiply that by the millions of fridges and freezers around the country, and if they all sort of went on low power mode for a couple of hours, that's going to save a good amount of power, hopefully, or better allow it to be sent out in other areas. So these things could, a smart device could sort of work in a more intelligent way. And even if you start putting things like batteries into these, they can store energy on a low cost time. They can sort of store solar energy, you know, sort of the grid energy, whichever, inside them, which is where people like Tesla company are going. They're sort of developing these things in their own sort of devices. Now these things, yeah, these are just some ideas of the local data processing that can sort of come in. I mean, there's some other ideas there about smart cities and the like, but there's quite a few things sort of going around it. But the data access to these, typically you're not just storing the actual reading, you want a lot more of that gathered data around it. Rather like that sensor data object that we talked about in the labs. You're not just storing the sensor name and the value, you want something, say, about its location, the time of day that that's occurring, perhaps a whole region of others like units that it's measured in, a range of values, what's its sort of accuracy, those sorts of things. So queries to that sort of data may require a bit more sort of information stored about your sensor and how you broadcast things out. And typically, these IoT devices using this publish-subscribe model that we've been doing again in the labs where you're doing your MQTT to sort of do it. So here, for example, we've got a bit of sensor data, 15 degrees. That might be meaningful. If I said, well, the temperature outside is 15 degrees. Yeah, that's fine if it's Manchester. You expect a temperature around that. If I was in Saudi Arabia, say, somewhere just on the edge of the Sahara, and I said the temperature outside is 15 degrees and it's midday, well, you might be a bit more worried about that, because if you never get down to that sort of temperature at midday for it. So you don't just want the value, you want some sort of spatial and temporal data perhaps sort of going with it, so that you know a bit better about what that data is in terms of how meaningful the data is, together with things like precision and accuracy, all these sorts of things being stored with it. So when you're coming around to storing the sensor data, you've got to bear in mind that it's not just the actual sort of value. As I say, if I gave you out some sensor data there, and said, okay, well, here's some data, how relevant is that to it? You know, what's it mean? You can be sort of guessing at that. You might sort of guess, well, because I know Nick's just been talking about temperature sensors and things like that, I'll take a guess that that 15 is to do with a measurement of temperature, and that the C is Celsius. Great. I'm taking a sort of guess there. 0815, well, that looks like a time, yeah, I'll sort of guess at that thing for it. 51.24 minus 0.58, what does that represent? People don't often carry around latitude, longitudes in their heads. That's the sort of latitude, longitude of MMU there. But without some sort of explanation of what those are, you don't necessarily know what each particular component is there for it. Is that latitude and longitude, or longitude and latitude? Is it the average temperature over the last year? Is it the minimum maximum temperatures over the last year? You know, last year it reached a temperature of 51, very unlikely, sort of thing. On the lowest temperature was just below 0. For it. Is the 0815 the time that the reading was taken? Is it the time that the sensor was turned on? But you don't really know, basically. You're starting to do assume, if you like. You're starting to assume things, and you got that old cliche about assume makes an ass out of you and me. It's just sort of, you've got to decide what those sort of values mean. So you've got to attach some sort of metadata with that, some data about that. Now we're just going to have a look here at intelligent processing, but next week we're going to have a look at how you might annotate that data. The sorts of things, again, that we're doing in the labs, annotate it either with XML or JSON, something like that, to better describe and give some meaning to that sort of thing. The data that we send out, you've got data and some of the sort of issues and problems that we're dealing with. You've got some problems of data coming out in different formats to it. Not everything's nicely broadcasting this out in one particular format. Some might be sending it out in Bluetooth, some might be over the Wi-Fi, in terms of protocols that it's using. But also, are they all using JSON to send their data? Is it just raw data in some cases? Is it XML in other sort of cases? How do you find where these devices are? This particular one, when it fired up, the example, When the app starts up, it asks each one of these to basically report on are you there or not. And if they're not there, it doesn't display control for it. As it turned out, when I first came in this morning, some of these weren't correctly plugged in. Just had to push them in a bit better. You saw that the light wasn't coming on. That's probably one of the wires out at the back of it. But this discovery and finding the devices and data sources can be a bit of a problem. And sort of access to get there. How do you actually find it? How do you query that data? Who's going to give you that data? Is it available from the device itself, or is it you querying some sort of server-side thing for it? Again, relating that to the assignment work, if you want to query the data, we're storing it in a table somewhere. You're storing it in a table over on that, say, Tomcat server, and then you're offering some sort of interface to be able to retrieve that coming back. And all these devices, they're all heterogeneous. They're all different to it. They're not all the same. They're not all necessarily from the Fidget library. So you've got the sensors from a huge variety of sources. Some might be physical sensors, some might be people sensors, that sort of idea. So dealing with integrating different devices, different networks, different types of data, and how you might interpret that data, how you might scale up to it. Again, all these are sort of problems that you're going to have to deal with in IoT bits of data. This might be, say, a chart here measuring some sensor data coming in. It might relate to, say, noise level in say, a particular room in your house. It might relate to temperature in a room in your house, sort of thing for it. Now, you can see there that it's spiking all over the place, and we need to know perhaps a bit more, sort of thing, well, what's the interval between each one of them. It seems to sort of spike up fairly regularly. Now, you're trying to read patterns into that data. And if I asked you to try and predict where this thing would be going, you might try and sort of draw a line through it and predict where it's going through. And that value that's circled, is that a sort of valid piece of data? Is it just some sort of aberration, something that's cropped up? I mean, if this is like a heat sensor, it may just be that somebody's held a match under the actual sort of sensor. I mean, that's a bit of an extreme case, but it's detected something exceptional in that sort of thing. Now, that can either be that you want to ignore those outliers, or it might be something that you want to focus in on and say, well, something special happened there, let's sort of work with it. So we're going to have to sort of deal with this sort of overall patterns of data. Now, compared to other data streams, you're always streaming, say, videos, music online, and those sorts of things. These data streams that are coming from IoT devices are quite different for it. And these are some of the sort of differences for them. The size of these things. Streaming video music tends to be very large. Tends to be very large files that you're streaming. IoT tends to be tiny. The location of it for IoT devices, that does matter. Just where it's coming from. If that temperature device is reporting 15 degrees C, is that coming from, as I say, the Sahara Desert, or is it coming from the centre of Manchester? Cheers. Where's it sort of appearing? Whereas for video, you don't care where it's coming from, so you sort of get the location of the source generally doesn't matter to you. Time dependency, again, not necessarily relevant to streaming your video in. It doesn't really matter what time of day you're doing it, but it does matter for IoT data. You tend to have a single data stream coming in, one or two data streams coming in for conventional ones. You've often got a very large number of these coming through. Video data, media data, persistent. Some of the IoT data does need to be persisted, not all of it. Again, relating to the assignment there, you're recording. What are you recording for these attempted door openings? Are you recording everything, or are you just recording successful values, or just when the door opened to it? So what are you actually recording for it? Are you recording every single value, or just the odd part of them? And what sort of resolution have you got for that? What sort of accuracy have you got for it? Now that thing does vary for your video files. You've got your MP4s, your MKVs, your AVIs, MP3s, all these sort of different ones, and the resolution is typically based on that file name in some way, what sort of resolution you're using. And again, the resolution of the data coming from IoT might be, you have to have some way of indicating what that resolution is. So it's not necessarily the same way of, in fact it just isn't the same way of dealing with the data stream that it is with these sort of standard ones. We're having to connect together these different types of devices. Either we've got these wireless sensor networks that might be collating the data and then sending it over to be sort of stored. Some might be sending it off directly. You've got to provide access to the outside world to that. Again, with your assignment there, you've got your sensors storing data inside your tables, and your Android device getting access to that, or a web page getting access for it to sort of work there. So there's a variety of things that we need to sort of consider in doing this sort of data processing for it. Finding out where that data is, who's actually storing it, what resolution they're doing, and typically we are going to need to do some sort of aggregation or bringing together that data. Now, whether that's done by the actual sensor device itself, the node itself, or whether it's done by this sync node bringing some together, or whether it's done on the server, again, it's application dependent. A typical example that you want is this idea of aggregation, where you might take, say, just the average of a set of values over a certain sort of time. It may be that you might want things like the minimum or maximum, or the sum of values. Like, if you're talking about rainfall, you in fact just want to know the sum of the rainfall in the last 12 hours, or the last hour to get through it. Where average, you're not going to take the sum of all temperatures. In fact, you're going to take the average of the temperatures, perhaps over a sort of given time. So you need to apply some sort of aggregation to that, dependent on the application to it, dependent on where it is, whether or not the sensor can aggregate it or give you a set of those before it sends you, or you've got some sort of hub that's doing that aggregation for you. You might want to exploit some sort of temporal values, because some values only vary slowly in time, so you don't necessarily need to transmit all the data all the time. Temperatures are a typical thing for that, outdoor temperatures. It doesn't suddenly go up from 21 degrees C to 45 degrees C outside. You don't need to be measuring that temperature every second, say. You only need to sample that temperature every now and then, so that you can sort of take advantage of both sort of where you are, when you are, perhaps taking into account neighbouring nodes to sort of do it. There's several sensors sending out values, bring together those and only transmit back the differences in those coming out. You might have all these temperature nodes scattered about a city, and one of them happens to be spiking, that it's very high. All the rest are reporting, say, 29 degrees C, and then one of them seems to be reporting 45 degrees C. Is that a faulty sensor? Probably. Or is it just something that has a fire going on there that's causing that? So signals from neighbouring nodes are generally quite similar. You might just want to look at sending these sorts of differences to it. The idea is that the network here tends to be data-centric. It tends to be concentrating on that data and thinking about what data to send. Because you're trying to improve your networking overall effectiveness. You don't want to be transmitting too many, because just bear in mind that these nodes are generally battery powered. You're trying to conserve power all the time. You're trying to keep the amount of data transmission to a minimum, but transmit enough to make your data relevant to it. So this data-centric network tends to be fairly important, because the data is both transient, it's time dependent, and the data quality might vary to it. How you actually find those resources can be a challenge. As I say, well, with some of these sensors, perhaps sort of going in and out of, sort of the mobile sensors, they might be going in and out of range, the battery might need recharging, that sort of thing. And we will have a look at it later on. But typically what you're trying to do is do some sort of aggregation of that data, either sensor-based itself or in a sort of sync gateway node, something that brings together values from it to avoid too much transmission as the sort of data comes around. So you might have multiple sort of sensors, and those sorts of the ones in the centre are the ones that are picking up values. You get the different values coming out from all round, and it decides to aggregate all of them. They all seem to be issuing, say, a value of 1 out, and then you get the odd one that's sort of seeming to do a higher value, and which one we send back to base. You want to just do an aggregate by straightforward average and say, well, actually, although one seems to be reporting a high value, I'll assume that it's just 1 for this sort of situation. It's very much application dependent. And in other cases, you might want to say, well, this seems to be doing something that's way out of range to it, and that's something to take note of. That, if it's a temperature sensor that's suddenly detected a very high temperature, then that might actually mean something. If it's a value that wouldn't actually occur, a wind speed of -8 or something, negative values perhaps so they don't occur in something. There might be something you want to just ignore for it. But the efficacy, how good something is, how well it's performing its job, can depend on things like the accuracy of the data that you've got. How complete is it? Are you sort of taking all values in there? What sort of latency is there? How current are these values to work with? And actually that last one, the overhead, the actual aggregation function might take some time itself. If you're reporting values back out, if I'm having to sort of perform some sort of aggregate, say on people in here, you might all transmit to me, say, your age, and I'm wanting to give out that average age. The time taken for me to record all those values, calculate the average and send it out, if I have to send that out, say, every second, I can't actually do it that fast. If the actual act of doing the aggregation affects the actual sort of processing itself, you've got to have some sort of trade-off between the sort of values as well. But typically it happens close to the source. And as we've, again, hopefully found out in some of the labs, a typical way of broadcasting this data out to interested users is through some sort of publish-subscribe mechanism. MQTT is one such one. We'll look at it in a bit more depth in a couple of weeks. We'll have a look at all these sort of aspects of it. But we've sort of looked at this conceptual idea of where we've got something in the middle relaying out messages. That somebody's publishing the data, some sort of sensors picking up the data and broadcasting it out, and others interested in subscribing to that. Maybe sort of software subscribers that control a motor, control a light. There may be a subscriber that's on a server somewhere, picking up that and bringing together the average and then dealing with something over a sort of a period of time. Now we'll have a look at this, let's say, MQTT a bit later on, but that's basically the way that most of these IoT devices do transmit the data. We do have something occasionally with time series data. Perhaps anybody who's done any statistics in the past might have come across these things called time series. Values that occur over a sequence of time. So you're recording values every second or every minute, and we get a sort of graph with time going along the bottom, and the actual value going up the y-axis, if you like. So we sample data at a particular rate for periodic data, and we can often use time series as a way of aggregating the data again, or even predicting where things are going on. The problem is that the sheer size of the data can be this sort of problem. If you're broadcasting out a lot of data, you often want to take a whole big long time series of your the sensor might have sent out 20,000 values in a day to it, and it's sort of, you know, you're recording these every 5 seconds or something like that, or whatever the difference will be in that. And what you're trying to do is to reduce perhaps the dimensionality of that data, to say, well, how can I reduce 20,000 values into maybe 200 values to it? Something that sort of summarises still the overall pattern of the data, because that data is going to be sort of varying throughout the day, and you don't just want to necessarily do a straight line through it, but you want to be able to summarise what that data is. So you're trying to reduce the size of the data and look for patterns in it, detect anomalies, ignore certain ones, or take certain ones into account, and try to transform a data series of n into a data series of length w, say, w being less than n. The net idea being that what we're trying to do is transmit less data. You're trying to not transmit 20k of data, you're trying to transmit, say, 200 bytes of data instead. Trying to really sort of cut it down. Now there's various techniques just sort of cropped up. And the technique that's described here, we're not going to have time to sort of go into today. I want to leave it for a bit of background reading, but there's one of these techniques called this symbolic aggregation approximation. Is really to represent a whole long series of time series data by an actual string instead. It turns a series of numeric values, say, I don't know, as I say, sort of 5,000 numeric values, into something like a 10-character string. And we can then start to compare these strings a bit easier. It's very hard to compare one time series against another without some sort of way of representing it. And this particular technique is to get a symbolic representation of time series, and then we can compare them. Now, as I say, I'm not going to necessarily sort of go through it right here. The techniques are just sort of covered in the following pages to perhaps turn a sample of, say, length 20 into just using 10 symbols, how you might represent that string of data, that time series of data by a string for it. The point about using strings and this particular technique is that similar time series end up giving similar strings. So you can sort of approximate that one time series looks pretty much like another by what it begins with. I mean, like the top one and the bottom one are so similar that they actually are the same, sort of thing, if you like. But it's easy to compare strings and how far similar they are, whereas that second one is very different to it. Now, the technique in here, as I say, I've not got the time to sort of go over it here, but it takes you through an example of taking a sort of time series of data, a very simple one there, just at 10 values, and how you might calculate this sort of n value to sort of get to it. Not necessarily of relevance, certainly not to your assignment, so not necessarily you'd be using it there, but if you're doing some sort of project that involves sending large pieces of data that might follow time series, you might want to look at some of these techniques as a way of shrinking your data down to sort of use it with it. The example work through, and that reduces that sort of time series just to a sequence of letters. Again, not sort of going through right now. And then there's a little bit about how you might sort of try this sort of thing out yourself. Take some time series and see if you can calculate it out. I've got a solution to that. If anybody actually does do it and want the solution, just drop me a message and I'll do it. We'll leave it there for today. We'll talk about estimating these two. So if you didn't sign your register, you've got it here. I'll leave it at the front just to click sign and it'll go out.
To be honest, it's because I've been
It's just when we've got people sort of coming in and I've got to pack this away before we get in, so I can't actually physically talk to you right now.